We, Jupiter, a red dwarf, the Sun, Aldebaran, Betelgeuse, UI Scuti. But let's start from the beginning. To go from something that doesn't shine, like a planet, to a body that is a source of light like a star, you need mass, a lot of mass. 70 times Jupiter. That's the minimum mass equivalent you need to gather to light up the smallest star it's possible to make. Barely 30% larger than our gas giant, but much denser. And above all, massive enough to produce its own energy, when the temperature of its core reaches 2 million degrees. Between these tiny stars and our Sun, we find 85% in number of the stars that exist. And if we compare a star of this type to our Sun, then it takes on the aspect of a giant, because it is 10 times more massive and 100 times brighter than Proxima b, the star closest to us. In reality, 85% of the stars that populate our sky are less massive than our Sun. A yellow star, which is almost halfway through its life and will eventually become, in a way, larger than itself. In 5 billion years, it will look different. It will start to expand to typically resemble something like Arcturus, a so-called red giant star. But don't be fooled by its size, because although it's 24 times larger and emits 180 times more energy than our Sun, Arcturus is barely heavier. This star's immense size is due to its age. Older than the Sun, it has entered a phase where its core, with age, has increased in temperature and ended up expanding its outer layers. Just like Aldebaran, which upon entering an advanced red giant stage became 500 times brighter than our Sun and 20 times brighter than Sirius. A star that, although 20 times smaller, is nonetheless 3 times hotter on the surface than the imposing giant. Sirius is also much younger and slightly more massive. Give it a little more time, and it will become larger than Aldebaran. Because as they age, all stars whose mass is between 1/3 and 8 times that of our Sun will begin to expand at the end of their lives, shifting to the red, and by ejecting a large part of their matter, they will give off planetary nebulae, forming in a few tens of thousands of years splendid structures of expanding matter, made up of their outer layers expelled by the rising temperature of a dying core that is shedding its gas mantle. In the case of the Sun, half of the initial star's mass will thus be expelled and will drift in space. The other, at the center of the nebula, will end up trapped in a white dwarf. The ultimate stage of evolution of all the stars we just talked about is 96% of that of our universe. The fate of all stars whose mass is less than 8 solar masses is to end up as a bare star core, a dead star without its own energy source that shines only from stored heat and will slowly cool and extinguish over dizzying lengths of time. White dwarfs only reveal their strangeness when observed on a scale, as up to 1.4 solar masses can be compacted into a volume barely larger than Earth. The matter is so concentrated that it has reached a so-called degenerate stage, to the point where the volume of a spoonful of this star weighs nearly a ton. Aldebaran is therefore just a temporary giant that will end up as a dwarf, although it already is compared to Rigel, a blue supergiant nearly twice as large and especially 10 times more massive and 80 times brighter than it. Rigel, a member of the exclusive Hypergiants Club, is at the start of a brief life. Because this space monster, due to its mass, will continue to grow by a factor of 10 to the point of quickly resembling Antares. A red supergiant at the end of its life, a kind of apocalyptic vision of the inevitable fate that awaits Rigel. Although the surface temperature of this star is lower than ours, it is so large that it emits between 75,000 and 100,000 times more energy. A figure that varies greatly, as its waist size does just as much. Antares swells and contracts as if it were breathing. And its radius can vary by in a few years. If you put the Sun next to it, you would have a hard time distinguishing it. And if you replaced it at the center of our system with Betelgeuse, then the radius of this red supergiant would extend to Jupiter. As for us, we would be inside the star. And practically the entire solar system in a plume of gas ejected by the underbrush of the star, which has become highly unstable due to its mass. As UI Scuti reminds us, with its radius 1,700 times larger than that of our Sun, it is the largest known star. To get an idea of the prodigious size of UI Scuti, imagine that all proportions kept, if the Earth had the diameter of a 2-centimetre marble, the Sun would measure 2.20 metres and Scuti 40 kilometres. Yet, this red hypergiant, which puffs out its chest, is nonetheless only 10 times more massive than our star. It is thought that its enormous size is due to the fact that, in the first part of its life, it ended up expelling more than half of its mass, which now envelops it in a burning veil of gas. Rigel, Antares, Betelgeuse, and Scuti. Without exception, all will end their lives in a colossal explosion. By transforming into a supernova, they will produce as much light in a few days as 100 million suns. The outer layers will then be propelled into space at staggering speeds, while the matter in the core will implode, the nucleus collapsing abruptly on itself, leaving in its place a residue of dead stars 20 to 40 kilometers in diameter. A neutron star, a tiny celestial body that could almost fit within the city limits of Paris and weighing more than our Sun. These stars, the smallest we found in the universe, are paradoxically heavyweights. Here, we find compressed into a sphere between 0.4 and 3.2 solar masses. The density of the matter that makes up this star is so extreme that it compresses the equivalent mass of 100 Eiffel Towers into the volume of a grain of rice. 4% of the stars that populate the sky, all those from 8 to 25 times the mass of our Sun, will end their lives as neutron stars. Those even heavier are extremely rare. In our Milky Way, we only know of a small handful, including Zeta Puppis. This star is barely 20 times larger than our Sun, 4 times smaller than Rigel, and 35 times that of Antares, in front of which it would almost pass for a dwarf. But once again, in the land of the giants, don't trust appearances. Like for boxers, a star's category is not inscribed in its size, but in its mass. Zeta Puppis is a heavyweight. It is more massive than all the stars we want to talk about combined. And its surface temperature is 4 to 12 times higher, which makes it one of the hottest stars in our entire galaxy. Zeta is to our Sun what a campfire is to a forest fire. It emits nearly 800,000 times more energy than our Sun, and if we placed it in the place of Proxima, the star closest to us, it would cast marked shadows on Earth. Zeta is located 1,400 light-years away from us. A distance, however, close enough for it to become one of the brightest stars in our sky in a few 100,000 years, when it will have expanded and transformed into a red hypergiant before exploding into a hypernova. Emitting more energy in a few hours than 100 million suns combined, it will appear in the sky more intense than the full moon and should be visible from Earth, even in broad daylight. For Zeta, as for all stars whose mass is greater than 25 times that of our Sun, there is no way out. The end is known from the start. It takes the form of a dazzling explosion and a collapse that will end its story by leaving a black hole in place of the heart. Such is thus the inevitable fate of a star on a mine and that of the pistol. A blue hypergiant, 2.5 times smaller than Antares, but especially 10 times heavier, and which produces in 6 seconds as much energy as the Sun in a year. In other words, our Sun is to the pistol what a lighter flame is to a forest fire. As for R13601, although 10 times smaller than the pistol, it emits 8,700,000 times more energy than our Sun every second. Its surface temperature is so high that it appears to us as blue-violet. This is the most massive star that has been discovered, heavier than all the stars we just talked about combined. If you were to place it next to Antares, R13601, although 20 times smaller, could pose a big problem because being so massive means a short and spectacular life. Especially since it's a so-called Wolf-Rayet star, producing so much energy that it has become the scene of internal instability that tears it apart by propelling some of its matter in the form of solar wind, which can reach 1/100th of the speed of light. This star swings in space, every 100,000 years the equivalent in mass of a sun, enough to blow away a large part of the giant Antares. And then, although at the dawn of its existence, R136A1 is already about to die. It's a colossus with feet of clay because its mass is its Achilles heel. The lighter ones, red dwarfs such as Proxima b, can shine for thousands of billions of years. Our Sun will only live 12, Sirius 1.5, Rigel barely 10 million years. The pistol wore more than 5, a snap of the fingers on the scale of cosmic times. As for R136A1, although barely 300,000 years old, it is almost already dead. Because like some rock stars, it burns fast, shines bright, and dies young. And in its case spectacularly, it will explode into a hypernova, a cataclysmic event during which it will emit as much energy as 100 combined supernovas. And after R136A, it's hard to go further. We've reached the top of the melting ladder, where the rare stars of 300 solar masses are precariously balanced. Today, in the universe, stars of this type are a limit, because we think that gas clouds, which ignite stars when they collapse, are not able, due to their composition, to make heavier ones. But there was a time, far back in time, when conditions allowed for the creation of even more massive stars. These formed when the universe was smaller and denser. From the collapse of prodigiously immense gas clouds, stars that we will never see again, because the conditions for their formation have disappeared forever. It is thought that there may have existed in these distant times stars with more than 1,000 solar masses. The most imposing were therefore also the first to form in the universe. So where are they today? The answer is they are no more. None of them have made it to us. All of them burned the candle at both ends quickly. Some must have even been so heavy that they may not have even exploded. All their matter ending up directly in the heart of a black hole. By sticking and comparing all these stars, one might end up thinking that they are close to each other. So let's keep in mind that if the Earth was 1 millimeter in diameter, the Sun would be a ball about 10 centimeters and located 10 meters away. The star nearest to us would be located 2,435 miles away. After all proportion kept to the star, if I had this size and my density, I would collapse, then I would light up. Thousands of tiny twinkling points, more or less similar, weak in intensity and close, or bright and distant. Their distance from us plays tricks on us, but looking closer,